Are you see my screen or not?
Oh, yeah.
And now it's fine.
Yes, now we do.
Okay. So I can, actually I can.
Yeah, so welcome, Anton, and thank you for accepting the invitation for this keynote talk. And Anton is the professor and the dean of Faculty of Control Systems and Robotics of ITMO University, and is a prominent researcher in many areas of control engineering. But without any further ado, Anton, please go ahead and start your talk, and welcome again.
Thank you very much for microphone. And now I want to show a few slides of our last results in adaptive control. My topic will be devoted to permanent magnetic synchronous motors, and a few results, a set of results, which will be combined in this presentation, may allow us to make a step ahead, step forward to so-called sensorless control. For sure, sensorless is like a game of words, and actually sensorless means we do not measure the regulated variable, and we try to reconstruct the regulated variable and then try to control using some estimates. And now I will go to the basic concepts of control systems. The classical approach tells us that if we have the plant with a regulated output variable y of t and some set of state variables x, we would like to design state controller which produces the control input u of t, which drives the plant in desired behavior. And we have well-defined output regulated variable. In fact, the state variable may be infinite dimensional and for sure available for measurements. For most cases, we may forget about x. And we go to the class of controllers, which is output controllers, which include inside some probably state observers or the derivative observers. But the practice is such that we usually use the measurements of regulated variable, which is output, and using this information, we try to design the control. And what to do in this situation if output regulated variable is unavailable? For example, we have electrical drive, like motor. The output regulated variables is mechanical variables like position, speed, speed of rotation, but all mechanical variables are unavailable for measurements. And input for such plant is electrical signal, for example, voltage or current in circuits, and how to compute, how to produce electrical signal which drives the motor such that mechanical variables unavailable for measurement will be in desired behavior. And this is the challenge actually for output control design. And in this, the next step, our conjecture that we will be able to design the output observer, the observer of output variable y, which is y hat, which will be used in output controller, which will be designed further. And this is the sketch of our idea. So we will try using the control inputs. We will use control inputs to reconstruct the output. And as I mentioned before, the main focus is devoted to electrical motors. And synchronous motors very popular setup in a lot of applications like cranes, elevators, pumps, even drives in manipulators. Synchronous motors very, very popular and widely used in industry. And the problem which I would like to tell is not artificial. Actually, using sensors in such applications brings a lot of problems. For example, long cables which used for data transmission bring some noise, troubles, and you would like to avoid cables, like make a jump from Ethernet to Wi-Fi, because you would like to make your system more flexible, more reactive and robust. And robust is also the second point. For example, if you have for example, aircraft with electrical drives on the very high altitude, all sensors becomes freezed and becomes not precise, and noise which produced by your sensors make problems. And that's why the sensor control becomes not robust. And this phenomena is very surprising, was for electrical community, but this direction of control design was opened a few years ago, maybe 10 years ago, maybe a bit bigger, but the main point is how to avoid using mechanical sensors and stay in good performance controlling this kind of plants. And basic approach for electrical drives, maybe look, you may see here. We have electrical motor. We have some electrical inputs. Usually it's three-phase electrical line. And we would like that this motor will make rotation with desired position diagram and desired speed. To design the control systems, we usually use measurements of real rotation and real position just to design speed position controller. And also we need position in some transformation, which is Park transformation, which is necessary to design very popular control loop, which is given here. So speed position controller allows us to compute some desired current in special coordinate, in special system of coordinate, and then special current controller produce necessary voltage on all electrical lines. And this is quite complicated, but very typical scheme is used in almost in all application. And now, what to do if we do not have mechanical variables? We go to adaptive observer problem, adaptive observer design problem. So we need mechanical variable here in Park's transform, and we need theta, which is position or angle, and speed, omega, in speed or position controller. And we do not have such measurements. We have only some information about electrical signals, which is current and voltage. So that's the point. That's the problem formulation. Let's design the speed or position controller for permanent magnetic synchronous motors using only electrical measurements like voltage and current of the starter wings. And now let's go to the mathematical aspects of this problem. Is it possible or not? In this reference list, you see some theoretical or historical background of this problem when we start to design new adaptive observers starting from permanent magnetic synchronous motor, when we try to find new effective observer of the magnetic flux. It was immediately published in Automatica because experiments was successful. And then we tried to improve the quality of our adaptive observer. We invented approach DREM, which is dynamical regressor extension and mixing. And it was also appeared in a very good journal, which allows to improve, substantially improve the performance in observer design or estimation schemes. And later, it was proposed adaptive observer based on this technique DREM, which allows to reconstruct state variables of nonlinear system very fast and with restricted requirements. Like literally, we may do not require any more persistent excitation to a regressor, and we found the necessary condition, because as it's well known that persistent excitation condition is sufficient and not necessary, and we found necessary condition, and we found how to design observers such that it will be effective even in restricted conditions. And then recently we published the combination of these results in one journal with experimental results for permanent magnetic resonance motors, DREM-based adaptive observers with finite-time, where we show how to reconstruct state variables in finite time. An arbitrarily small finite time, we may reconstruct the state variables with zero error. And now there are a few ideas how to do this. If we consider the model of the motor, system of equation 1, we will see the equation for the magnetic flux lambda with voltage V and current I. R is the resistance, and alpha beta means that we have two-dimensional vector. Alpha beta is two-phase frame, which is maybe obtained using Clark transform from any phase machine. And the second line is the Newton equation, which describes mechanics, which describes dynamics in the motor. Where is this? Omega is the speed. This is viscous friction. This is our electromagnetic torque and some load torque. And theta is an angle. And look into this model. We want to reconstruct the state variable lambda, which is unavailable for measurements, and we measure only current and voltage. For surface-mounted motor, which is also non-salient, where special conditions for inductance, we may use the expression 2, which holds for magnetic flux. So magnetic flux depends on the current and the position of the rotor, which is theta. And from this expression 2, one can reconstruct theta using equation 3. So taking inverse trigonometric function with respect to variables, one can reconstruct theta, electrical angle of the motor. The question is how to reconstruct magnetic flux. So that's the problem. And the goal is to design such controller which is based on estimate of magnetic flux, and such estimate which is equivalent to the real magnetic flux after some moment of time. And flux observer, maybe I will show the idea shortly in one slide. We will use such expression, which was shown before, where C, capital C, is cosine and sine, special vector of trigonometric functions. And then we may compute that using basic trigonometric equation or Pythagorean theorem, we may exclude angle theta, like cosine square plus sine square equal 1. And this is identically coincides with this expression 5, where we have magnetic flux, current, and some magnetic flux from the permanent magnet. And then if we apply the filter, where P is the differential operator, so first order filter and plus one time derivative, we may obtain the expression 6, where you may see that this is maybe computed, this term may be computed, this term may be computed, and we have the problem, we have to apply first order filter to the production of unknown lambda and measurable signal, electrical signals, together with unmeasurable time derivative of the current. And from this point, we found very easy way out. Actually, so-called swapping lemma was appeared in works of Stephen Morse in classical adaptive control framework. But the main idea which we need, we have linear operator H, which is applied to the production of two functions of time, and we would like to pull out one of them. So we would like to pull out phi from this operator H. And you see that it's possible to rewrite this expression like linear operator to omega, to W, multiplied by phi, where phi already pulled out from this operator H. But additional term will appear, which depends on time derivative of phi. That's the expression, which is very simple in if H is the first order filter, like we use. And if we use first order filter like this, it's very simple to rewrite previous equation to expression 8, where everything is computed and lambda already independent on computed signals and explicitly written in linear regressor form. And now, if we look to equation 8, we may rewrite it in more compact form, like Z is a available computed signal, G is computed signal, and lambda is the vector of the flux, which should be reconstructed. And Z and G depends on our coefficient alpha, which may be chosen as we want. And if we will choose different gains alpha, we may reproduce this linear regression several times. For example, we take two different alphas and we get two linear regressor equations with capital Y, which of two Z's and capital Q. This is the extended, so-called extended regressor. Actually, we combine two regressors and we get dynamically extended regressor. And then what we need to do the mixing of this dynamically extended regressor equation. And it's very easy to show that this matrix equation may be decomposed to the set of scalar equation with available psi, with available capital delta, and the main point that capital delta is the scalar. So determinant of this matrix Q, determinant of the matrix, is the scalar variable. Psi is the production of adjoint matrix Q and given matrix Y. And from this matrix equation, which was very straightforward, we get a set of scalar equation where scalar regressor equation where regressor capital delta is available, and we need to reconstruct only variable lambda. The next is quite simple. So using this delta and this is psi, we may design Lindbergh observer for these functions lambda. We know time derivatives of lambda. This is correction term. And using auxiliary variables W1, W2, we can write precise equation of finite time estimates. So this modification of those estimates gives us finite time estimates of the flux. And all requirements what we need: interval excitation for the variable capital delta, which implies necessary estimates. And now position and velocity observers may be written, as already mentioned before, using inverse trigonometric expression. And for reconstruct the speed, often you may found so-called phased locked loop type steep speed estimator, which is given in system 19, which gives estimate of omega, which may be used already in some control design. The most simplest controller which we may use is field rate control, which actually use some feedback linearization terms and allows us to choose some proportional and integral gains and design like PI controller, which is quite simple. But now let me show some simulations how adaptive observer works. We consider some real motor with real parameters, and we would like to repeat such desired speed diagram. And for example, pink line is a desired variable, a real variable. Blue line is our estimate, and red line is the error of estimation. So this is desired level and estimate. We see that so this is real angle, and this is our information about angle, what we reconstruct ourselves. And on the next slide, we see how it works with noise. But this is on the simulations. The most interesting part will appear very soon with real experiments. And we go to the second block, which is advanced controller for permanent magnetic synchronous motors. I mentioned before that very simple controller is field rated control, but we go further in our research and propose some new controller which may be interpreted like generalized PID controller. Generalized PID controller means that we generalize integral part and we will generalize D part. So opening some questions, I will say that generalized integral term is internal model approach, and generalized D term is the so-called extended observer proposed by Friedovich and Khalil a few years ago. And we will combine these two approaches, and you will see now soon how it works. So in our advanced control, we will consider that we will temporarily assume that theta is available for measurements, but currents, electrical signals unavailable. And we would like to design output robust controller, which allows us to design, which allows to regulate speed and position if we measure only output variable. And theoretical background, a set of work with Alberto Isidori and myself and my former PhD student Borisov Oleg. We proposed, it was appeared in Automatica, some modification of extended observer, so-called enhanced extended observer, with respect to famous result of Fridovich and Khalil. And the main contribution was that we consider the time variant system, and we design extended observer for time variant system using Dai-1's lemma. And then using this basic approach, we design advanced controller for permanent magnetic synchronous motors, and it was published in IFAC Congress previous year. And you may find this already all calculations and derivations in these two papers. The main idea is to use a geometric approach of Alberto Isitori, and the main contribution is that we found the change of coordinates 21 for model of permanent magnetic synchronous motor, where Xi1, Xi2 is the mechanical variable, and Xi3 the variable which actually has it is the bridge between mechanical and electrical signals, which is time derivative of omega, which is related to time derivative of omega. And you see that the Xi1, Xi2, Xi3 related to each other like chain of integrals. Chain of integrals with some gains G2, G3, which may be time varying. This is important. G2, G3 may be time varying in our approach. And Z is the so-called zero dynamics, which describes transients in electrical circuits, which does not affect to the output mechanical variable. But the rest of electrical dynamics will be hidden in variable Z. And using this change of coordinates, we may obtain system 22, which is nonlinear, and for which we would like to design extended observer in the frame of work Fridovich and Khalil. And it becomes possible, but before we would like to make Park's transformation and replace the voltage V from static frame related to the stator to the rotational frame, which related to the rotor in DQ frame. And then our model of the permanent synchronous motor of PMSM will look like 24, where Z is zero dynamics, which is driven by component VD, D component of the voltage, and all mechanical dynamics, which is driven by VQ, the Q component of the voltage. And all variables related is the chain of integrals and some nonlinear term on the input. From physical point of view, the zero dynamics is very fast because the coefficient is negative, which is here, because if we look to the F, this is Z dot equal this expression, and this is internally stable dynamics. And for example, we may make VD equal to 0. We may use VD like control and regulate the zero dynamics if we want, but we may relax VD, take VD equal to 0, and forget about internally stable zero dynamics and concentrate only on mechanical dynamics using VQ. And now we will describe what is generalized PID. Generalized integral component actually is internal model. The approach was proposed by Wonem 40 years ago. I'm sorry, maybe 50 years ago already. And internal model is the incorporating in the control loop the model which repeats the dynamics of the exogenous systems. For example, if we have disturbance or we have reference, and we know the dynamics which describes this reference or disturbance, we include the model of these exogenous systems in the control loop. And for example, here it's just rewritten in special form proposed by Isidori based on Nikiforov's lemma, the expression 25, which allows to incorporate in control. For example, VQ will be the output of this filter driven by nominal controller U by, and dynamics of this subsystem is repeating exogenous system. For example, if exogenous system has a constant disturbance, in particular case, if the disturbance or reference is the constant, the load is static, and matrix 0 S, which describes the dynamics of the exogenous systems, then this internal model becomes just a simple integral. So the integral is the particular case of the internal model approach. For example, if the load is sinusoidal, we will include the dynamics which describes the sinusoids to the control loop, and VQ is the output of the internal model, which is driven by nominal U bar. And nominal U bar should be designed with respect to the dynamics psi, independently on external disturbance or reference signals. And here we use, as I told before, the approach which based on extended observer with this contribution of the Leonid Friedovich, which is very important, additionally variable sigma. So we repeat dynamics of psi. We add some correction terms. We use some high gain kappa, and increasing k we achieve necessary stability results. And using this signal sigma, which is appeared in the last equation of psi 3 dot, we also extend this observer. And in fact, this is a generalized D component because this is the set of derivatives. This is first psi 1 is our output, psi 2 is the time derivative of psi 1, psi 3 is time derivative of psi 2, and etc. So this is the set of necessary time derivatives with respect to relative degree of the model of our plant. So this is generalized D. All derivatives that we want to use to get necessary controller. And now I will go to simulation results, how it works, combinations of internal model and the extended observer for the motor with real parameters. So without a low torque, with constant low torque, and with sinusoidal low torque. In all cases, our reference, our rotation angle goes to the desired value 1, error goes to 0, and we see that it works. So the theory, simulations just illustrate that theory works. And now generalized PID controller for nonlinear system maybe presented more general, maybe looks here. So using alpha, using measurements of the current, we may regulate zero dynamics, which is electromagnetic character, and using theta, we may use we may design mechanical regulation controller. And my main proposition is the combination of advanced observer of mechanical variables, which was generalized Kalman's filter or generalized Lindberger observer, and generalized PID controller for nonlinear system, which was represented before, with internal model and extended observer. So applying this concept to our problem, control of permanent magnetic synchronous motor, we may propose so-called sensorless controller. We already know that having only electrical inputs, voltage and current, we may reconstruct position and speed, and use advanced position controller, which based on one of them, or speed or only position estimate, may provide the convergence of our mechanical angle to the desired value, or tracking for the desired diagram for the reference. And real motor tests were quite interesting. We can see the real motor, which was provided by St. Petersburg company Diacont, actually international company with different representatives in different continents and countries. And we took the motor of this company and actually research setup. And we did with this company, Diacont, for 3 years, very big project. And actually, we was very I'm happy to say that we get necessary result in this project. And here we will see. So this is real measurements of the current, real measurements of the voltage, real measurements of electrical angle. And this is velocity, and this is error of electrical angle estimate. So on this diagram, this is real transients in a real system, and the first result that we can reconstruct the electrical angle in real experiment. And this is current voltage, electrical angle together with its estimate, and this is velocity. So we give some desired velocity, and we immediately repeat this estimate. And just to conclude my short presentation, I would like to say that we know how to design the state observer for some class of nonlinear system infinite time. And such class of system is, for example, electrical motors or manipulators, or even surface vessel motion, or unmanned airplane, unmanned aircraft vehicles like quadrotors. So it's become possible using this technique. Position of the synchronous motor we may reconstruct using an estimate of these states like Flux, and then we show how it works in simulations. But what we can also fix, we need only electrical signals to not only reconstruct the state, but also to design the controller. We have proven our result, our contribution in very good journals like Automatica and Transactions Automatic Control. And the most important for me result that it was implied in real electrical drive in big, very serious project with industry company. And we get necessary result. We can repeat all theoretical claims in real practice for industry guys, which is most complicated probably when everything is fine in MATLAB, and when you go to communication with real industry, you will surprise a lot. And we also get this level as well. So some additional comments you may see on these slides. So some properties of our approach, why our approach is interesting. But in general, actually, I'm ready to finish my presentation. And thank you very much for your attention. And if you have some questions, I will be happy to answer.
Thank you very much, Anton, for your wonderful talk. Really impressive, both the generalized PID and especially the practical experiments like you mentioned. I just wanted to ask, are there any questions from the audience? And while they're preparing, if you don't mind, I have a couple quick questions maybe from my side. So you're using the current measurements, right? Like IA, IB, as you showed on slide maybe 27, right? So how about practical, oh, yeah, maybe not here. In the schematic diagram that probably, yeah, so for a practical motor, you know, these measurements are usually very noisy, and do you have any like know-how suggestions on, you know, techniques that are required to filter this data and how this affects the performance? Yeah, here, this slide.
The idea is if we have, if the current available, if we know the current, we may design robustly the Q component, D component. If we will design the D component, we may accelerate, or we may control any performance that we want. But we definitely need measurements of the current just to control the zero dynamics. If we do not have current, we may, in this case, we need measurements of the theta. But in sensorless setup, actually, we don't have mechanical measurements, and actually we have only current and voltage. And using current, we may design regulation for zero dynamics, and we want to design for mechanical variables, for zero dynamics and for mechanical variables. And this is your choice. You do not need a lot actually for that, because everything is given here. Actually, the all dynamics is presented here. The D component drives the zero dynamics. The zero dynamics is explicitly written here. So the equation is obtained, and this is the situation. So if you want, you may control zero dynamics. If you may, you may don't care about zero dynamics, because this dynamics is internally stable, and Q component is which is necessary for us, because this is the main driver for all this machinery. I don't know. I'm not sure that I recognize correctly your answer, your question, but yeah, I think what to do if current measurable or not.
What I meant to say is, in practical motors, it's usually very noisy. Often the current measurements. So did you have this problem in your practical setup?
But in our practical setup, actually, yes. If we will see two diagrams, actually maybe not good performance, but measurements definitely with very noisy. But we aim to design our controller in robust sense. So we want to design a robust observer and robust controller. So we assume that we have noise. We are aware that noise will be always, and we achieve the desired performance. For example, like 5–10% of error in speed regulation, without measurements of angle or rotation speed. So the point is, we achieve the required performance in real conditions with real noisy current.
So you did not filter it; you used the measurement directly. Do I understand correctly?
In fact, our controller is a filter, non-linear adaptive filter, and tuning of parameters inside our controller actually is the repeating of this function of filter. So the functionality of filter exists in our approach. Moreover, I can say that the best performance which was obtained in this combination of our approaches was achieved when tuning of these parameters was given to machine learning algorithms. So we know, we prove the theorem, we prove the stability, we find some necessary condition, but the choice, the optimal gains was possible in practice, was possible when some literally adaptive optimization. Adaptive optimization gives the best choice iteratively, find the best choice of gains of our controller. And then I didn't include in my slides, but it's also very impressive. Then overheads disappear, when transit time becomes extremely small, even with noise and uncertain cases. So we give the core. We give the core of nonlinear dynamical controller, but some parameters which is necessary and which is used in this controller may be tuned using machine learning approach, and the result very impressive. So I think that future will be for machine learning based adaptive optimization of classical controllers.
Thank you very much for your kind answer, Anton. Do we have any other questions from the audience? If not, then I would like to thank Anton for your talk, and let us break for 10 minutes, and then we'll resume the regular sessions at 11:45. Thank you very much again, Anton, for finding time to talk here, and I really look forward to meet you in the future.
Thank you very much. Thank you.
Have a good day.
Bye.